We're going to talk today. Well, in my speech, I try to show something or try to teach something. I see people that know much more quantum than me in this room. Some of them. So if you are getting worried, please raise your hand and I'll try to move faster. But for the people that has no idea about quantum, what I will try today is to show you the difference between a bit and a qubit. What is quantum about and what kind of advantage it's going to give to the world in terms of computational advantage. We are talking today only computation, quantum computation, okay? There are, on the quantum side, there are sensors, also algorithms, computation, hardware. There are different fields. Today we will talk about the hardware and computation. Why quantum? Someone, well, at least in my social network, they don't know what's quantum, and they usually ask me, what are you doing with quantum? So why we need quantum? Well, there are plenty of problems in the world, plenty of them that we cannot solve nowadays. Some of them are so easy that we cannot, for example, multiply two big matrix, so big, we cannot multiply them. We need HPC, high performance computing. This is what I also am. I'm an expert in IBM, and I'm doing the integration of HPC and quantum. And for that kind of calculations, we need huge machines. So, for example, we have Barcelona Supercomputing Center here in Barcelona. Think that the old Barcelona, the Mare Nostrum 4, has 3,600 nodes. The new one has about 15,000 nodes. This kind of service is the one we use for these problems. I'm going to give you some examples. Well, how the molecules interact between them. For example, one example that I love, because we helped to create the flow of the air for airports. If you want to see the airflow through a whole airplane, you cannot know that with a digital twin. We cannot simulate that. What we do is we simulate the wings, afterwards we simulate the body, the head isolate, the tail isolate, and then we put everything together and we get assumptions. This is the powerful we have right now. There are plenty of other problems that we cannot achieve. This is the biggest one we have for IBM, in IBM technology, and we cannot afford small things. Small things is, for example, if we want to calculate how a medicine is interacting with a protein, with a virus or any kind of protein, what we do, usually we take 1 nanosecond and 1 nanometer, and we see how it interacts. Usually it takes around 1 year to calculate that, more or less. If you put GPUs and you use a cluster of GPUs, you can reduce that to a week, more or less. But then the researchers want more than a nanosecond. They look for a millisecond because they want to see much more interactions. And it's 1,000 times. So again, we are on a year. I can explain a lot of more problems we cannot solve. Monte Carlos, they arrive to a certain limit. A lot of more problems. So there are intractable problems. It's a science in research centers dedicated only to see which kind of problems do we have. There's an entire field for that. So these are the problems we can address today. We don't even know if we could address in the future. Problems we can address today perfectly, like looking the registers of a database, sending an email, doing sums, multiply. These kind of things are quite easy. And problems we hope we will manage perfectly with quantum. Which kinds of problems are these ones? These are the basic ones. Okay, it's plenty of them. But on the quantum side, which is what we are going to talk today about, things that the classical cannot do at all, even if they are superpower. I mean, even if you take a supercomputing of 1,000,000 nodes, simulating quantum mechanics is going to be almost impossible for classical. Factoring, well, it's polynomial, and the quantum, what is giving us, it's an advantage on the factor of the polynomials. So it's going to be easier. Sorry. No. And Jordi just told me that seems that the Chinese people is working on non-polynomial hard problems as well. Let's see what quantum can do. Okay, more or less, this is what happens, and this is what's behind the quantum. What we are really trying is to solve things we cannot solve today. And you mean, how powerful is the quantum? This is just an example. You probably, if you've heard something about quantum, you know this example. But this is factoring, one of the points I showed you in the previous slide. And this is the difference you could find between the classical and the quantum. Okay, so if you use classical to decrypt RSA, it could take you trillions of years to have the two factors, the two prime factors. Okay, if you use quantum, theoretically, it takes only seconds. We are forecasting hours because we are forecasting that we have in the cloud, so you have to send the data, you have to split it in different quantum computers, you have to pre-process and then post-process, and this is why we assume it's hours, but probably should be around seconds, the computation on the quantum hardware. Okay. This is the real difference, and this is disruptive. Think that every single communication you have, mobile, email, call, whatever, it's encrypted by RSA. Nowadays, the companies start doing some protocols that are quantum resistance, but just to let you know, or to have a feeling of how powerful is the quantum. Okay, and fundamentally, it's a new type of computation. What we have done since the first mechanical computers, and by the way, these are not the ENIAC, these are the IBM at the very beginning, before the early 90s. For counting the people for the census of the United States, they spent almost 10 years. So they start using tellers with the punching cards to do the calculations, okay? Electromechanical, that was same, zeros and ones, but with electric support. Instead of using a teller and doing it manually, you do it with electrical support. Then the vacuum tube, the discrete transistor, well, I'm not going to all of it. Nanosheets, right now we are in exotic materials to have the 2 nanometers transistors. But at the end, everything is exactly the same. We are talking about zeros and ones. So it's more zeros and ones, and more memory, but at the end, exactly the same. In quantum, we are changing. We move from bits that can be zero, either one, to qubits, which is an object. This is the minimum unit of information, and it's an object that can have different characteristics, and we use that object for doing the calculations. You know the classical bits, 0 and 1, you know the classical gates, AND, OR, XOR, XAND, and how they work. Which is the equivalent in quantum? And this is a question at the very beginning when I started in quantum, I really, because I understood very well the classical. So to know what's happening in the classical and compared to the quantum for me was very useful. This is a bit and this is a transistor. What does it mean? You have voltage or not. If there is voltage, it's a 1. If there is no voltage, it's a 0. And then you can play with the different discrete gates. The quantum bit is a qubit. And a qubit is an object, and you can have any value inside this block sphere. This is the block sphere, and this is how we represent the qubits. You can have any value. I will explain how powerful this is. but it's not just 0 or 1. And here we have also the Schrödinger cat. It's 0, 1, both at the same time, or 1, and we can play much more than the classical ones. And for the gates, we have also gates, but they are quantum gates. We have one gate, so 1 qubit gates, and 2 qubits or multi-qubit gates. And the measurement. These are the functions we have. Like in classical, we have a minimum unit of information, and then different gates for doing different operations. Which kind of operations we can do, or how we can work with the bits and qubits, or the qubits. So I explained, basically, it's a state combination. Let's take in account that we have 0 and we have 1 state, and we can have between the block sphere any combination of these two vectors. That means that you can work with any state. So imagine a vector, well, I will show you maybe. Imagine a vector like this. So you can point that vector on any point of the surface of the block, of the sphere. And that is a combination of 0 or 1. If it would be in the middle, that would be 1/2 of 0 and 1/2 of 1. Well, to maintain the probability is 1 over square of 2. But this is what it is. It's complicated. This is a more technical part of the speech. So then, when we apply the gates, what we are doing to that vector into the block sphere? We are moving it. If we apply an x, for example, we are doing a 180 degrees over the x. That means that we move from pointing to 0 to point to 1. If we have a Hadamard gate, what we are doing is moving, well, I'm going to tell this correctly, moving 100 over the z and then 100 over the x, okay? Over the y. And then you put the vector in the middle. When you measure, you have to measure the projection on 1x. If we measure on the z, you have to collapse all the probabilities. So the probability will collapse either 0 or either 1 in the moment of the measurement. Before the measurement can be both. It's both, in fact. The cat can be life and death. When you open the box, when you do the measurement, is when you define. Okay? Difficult? For some people, they are laughing. Some people not getting. Which are the characteristics we are using in the quantum with these qubits? We are using superposition. You saw that in the Hadamard, which means every qubit it's a superposition of different states. If we have only 1 qubit, it's a superposition of the states 0 and 1. If we have 2 qubits, superposition of 0, 0, 0, 1, 1, 0, 1, 1. Okay? With that, we can move into the block sphere all over the block and get different results. Measurement, I explained you. Once you measure, you get a result. Once you measure, you collapse the probability of the system. This is very important. And entanglement. Once I couple 2 qubits, they cannot be decoupled. Well, we can work with them, but they are coupled forever, even if you move them a long distance. They are doing that with photons, so they couple a couple of photons, they separate them. I think the most promising test is more than 100 kilometers, and they still entangled. So what you do to one of the photons, it's affecting to the other. Well, entanglement, I'm not going to be very technical, but basically, if you have more than one, you are entangled in the system. And interference. Why we use interference? Using superposition, you start making one state interference on the other. So you can or lower or higher the probability you want. And iterating that, you arrive to the result you want. That said, this is a circuit with different gates. I'm going to give a small test here. So if we have in 0 and we apply a Hadamard and we do a measurement, what we are going to have?
0 or 1?
One of both. Remember, you have the vector in the middle of the sphere, it has to collapse. We are measuring on the set axis, and then you will have 0 or 1. If you do exactly the same here, it's different. You apply the Hadamard, you measure, so you are defining here. You get a 0 or 1. And then you apply a Hadamard again. What you are going to have here? Same. Because you have not defined it. Once you apply the Hadamard, you don't define here. We apply a Hadamard. And then we apply another one. The Hadamard, remember, 180 on the set, and then move on the Y 90 degrees. Okay? We do again the same, 180, and then we move 90 degrees. We are going to be exactly on the same point we were. What does it mean? You can play with the states, you can do whatever you want with them, have a lot of superposition states until you measure. Once you measure, you have a result. In classical, this would be unaffordable because you cannot have all the states at the same time. You cannot play with the states. For playing with the states, you will need a memory register for any of each one. That it's you cannot handle that. Think about the number of states. It's true, the number of n. I will show you the numbers later. But imagine the number of states you are working with 160, for example, qubits. If you go to 300 qubits, you should use all the atoms in the universe to have the same number of states. Impossible. That's why the quantum computing is so powerful and cannot be achieved by classical computation, never. Well, we don't go to the examples because if not, we won't have time. And I want, at the end, what we are doing with the Hadamard is to represent this. Probably all the physics team knows this much better than me. So you are representing these operators and how we are doing that in a circuit. This is the circuit. I show you the gates, but this is how we represent the circuit. If we have time, I will show you. But at the end, I have the link to a URL where you can play with all these things for free and working with our quantum computers, okay? And this is how you program a quantum code. This is Qiskit. This is how we code it. This is a library based in Python, and it's very easy. So you are creating the registers, the classical registers. You need to create a classical register to put the results that you are getting from the quantum and creating the quantum circuit. Here you are adding a Hadamard, a C0 gate, and then you measure. This is how a circuit is created. It's quite easy. If you can go to www.ibm.quantum.com, you can find a lot of documentation on the libraries and can work. I will explain later, if we have time, some other characteristics of Qiskit that can give you more abstract value for the error correction, error mitigation, and also libraries for use cases, specific use cases. So at the end, this is what gives quantum computation to the world: superposition, interference, entanglement. With superposition, we have a lot of states, and to the end is the exponential information we can handle. How big is this? This is this big, exponential growth. So if we have 65 qubits, this is the number of states we can work with. With 275, that would be more state dimensions than the atoms in the universe. So I was talking about 300 more or less higher. But this is the number. So an example is, for example, the caffeine molecule. We cannot work with the caffeine molecule because it has 10 to the 48 different states. This is 10% of the total atoms of the Earth. If we could have a register just with one atom, we will need the 10% of the Earth. It's impossible. We cannot manage that. We cannot work with this kind of calculations. With 160, we could work. With 160 qubits, logical qubits, we could work with the caffeine. What means logical qubit? A logical qubit is a qubit that is resistance against error failures. So it's totally redundant, and we can work infinite time with it. Well, this is more or less what I want you to learn. If anyone didn't know anything about quantum, at least you know that there is qubits, there is bits, and the amount of states we can work with is unmanageable with the classical. So imagine if you need that kind of states in the future, things that we can do are going to be from digital twins that can simulate the application of any medicine in real, and then you can see how they act. And with digital twins, I mean with your DNA. So fully twin. It's like you, but virtual. And now what we have as IBM, which is the state of the art. Well, right now we are in different countries with different servers. These are the quantum computers we have all around the world and the planet for the next year. Fraunhofer, in fact, we are right now delivering another one there. Kawasaki in Japan, this is the university in Tokyo. We announced last week that we are going to have also a 100,000 qubit system in 2033 together with them. Cleveland Clinic, PinQ, we are working with them also for HPC. And these are, well, we are delivering that with a little delay. Jonsei already delivered. Iker Basque here in Spain is one of the hubs we are going to have. It's going to be the most important one in Europe. And we can discuss about it in the coffee break. But for me, the political in Europe is getting mistakes. Anyhow, this is going to have 127 qubits, so it's going to be the bigger one in Europe together with Fraunhofer. And Riken, also with Riken, we are working for 2033. These are the systems, these were the systems you had in the past, available for you for free. Right now, you can work only with the 127. In IBM, our aim is to work only with algorithms above 100 qubits. This is something that a simulator cannot do. So that, honestly, it's something commercial. We want to leave the competition behind. Sorry. We announced last year 1,148 qubits. So for us, make no sense to go to do calculations of 6 qubits, 7 qubits anymore. And I will show you later what's happening in the field of research. Anyhow, you can reach the 127. If you go there, you will have 10 minutes for free every month. Think that that means $1,000 for free for you every month. It's $1.6 per second calculation. This is around 100 per minute, more or less. 1,000 per month. You can just enjoy it. What quantum is good? This is what we were talking about. Simulating quantum systems. This is honestly what I see is going to be the future. If you want to simulate the nature, in the HPC, what we are doing is getting assumptions. We are getting the assumption that this molecule is going to behave in that way because 90% of the times it's doing that way. But we also have to take the assumptions of the 10% and we do all the calculations, and at the end we have a deterministic value. If you do that in a quantum computer, it's not going to be a deterministic value. It's going to be a real quantum mechanic value. What we are doing, I haven't explained that. The equivalent of the transistor is a transmon in superconducting technology. Sorry. I didn't explain that. And in a transmon, what we are doing is simulating the behavior of the atom, the behavior of the different energy levels of an atom, and that's what we are simulating. So That's why when you are using a quantum computer, you can not assume, you can just get the result that you will have if you observe the nature. Well, at least this is the aim we have, and this is what we think is going to happen in the next 10 years. And this is where we think the classical computers cannot compete, never. Then we have artificial intelligence. Why we are very good in the quantum computation in artificial intelligence? Because quantum is very good in probabilistic and also in conditioned probabilistic. So artificial intelligence use a lot of that. And also for Monte Carlo. For Monte Carlo, it's not just that quantum is very good in probabilistic, in conditioned probabilistic, but also is very good in randomness. So we can create real random variables where classic cannot. I don't know if you code in classic, but in classic, when I code in the past random, I use the third or the fourth digit of the time when you put a key in the keyboard. This is quite random for me. But even that, probably the same human has a pattern that can be reached for some good hacker or good observer. Randomness in quantum is very good. That's why it also behaves very, very well. And this is what we are doing with different enterprise. So what I want to show you with this slide is we are moving in the research field, only research, because if you want to find a use case where you can have a real advantage, right now we don't have. So we have it tested theoretically. And if you reduce the power of the classical, you can see that the quantum is more efficient. But we haven't got any use cases that is surpassing the classical, and that's because the number of qubits we have and also the error correction we have. But these enterprises, they are working with us because they see that in very few time, this is going to be a real advantage. So, for example, we are working with JP Morgan, and they are saying that if they have advantage, even if what they have researched, if they use in public for 6 months, those 6 months are going to give them super advantage in terms of earning money compared to their competition, okay? This is our roadmap, and we have two roadmaps, development roadmap and innovation roadmap. Why? Because lately we only show the innovation roadmap. So for example, Osprey, we show Osprey in 2022, and everyone thought that they can use Osprey. No, and we had Osprey. Osprey is a chip that has 400 qubits, more than 400. We are working with them, but we are not showing. So to avoid these misunderstandings, we split on what we are going to deliver and what we are doing inside our home. Because all the research field wants to know what we are doing also. What we are going to deliver in the next years. So the more important, well, in fact, Aaron was announced on November in the summit. I will show you later. But we are working with Eagle. These are names like Pentium for Intel, and that's how we call. And as you can see, all of them are birds, and Australian birds, because Jagan Beta, who is the executive, he's from Australia, and we are geeks, and you know. So we announced Aaron last year, and we are working with it. And if you connect to the quantum, platform, you can see the Aaron. Probably you cannot work. I can work because I have a premium account, but you can work with Eagle. Don't worry about that. Aaron. Why is important Aaron? For us, it's our battleship right now. Until 2023, the battle were on the number of qubits, how we are going to scale in the number of qubits. So we show the 1,138, and for us, that's the limit. Taking account that we want to arrive to 1,000 qubits. Osprey is like this, more or less. And Flamingo, no, it's Condor, sorry, it's a little bigger. It's like this. You can, so this is 1,000, and you have to multiply this for 100. It's not a scale. You cannot reach that. It's impossible. Think that this is a 12 millikelvin. It's colder than the space and these kind of things. But you cannot do a fridge for 1 square meter chip. Impossible. And also, the entanglements between the different qubits are very difficult to manage. So what we are doing is splitting and put different processors in parallel and connected by a couple that maintains the coherence. That means that you maintain the quantum state in 2 different chips that are communicated. Okay? For us, this is the partnership because right now, that means that this is an engineering problem. If you have the money, no one has the money to put a lot of iron together. But we are going to increase that capability and that density. But if you have the money right now, we have the technology to arrive to the number of qubits you want. What we are going to announce this year with Aaron again, well, this is the deliver. The announcement. This year we're going to have Flamingo that are going to have long couples. That means that they are going to be not just close one to each other, but they can be separated. So the number of couplings are going to increase exponentially. And this is the way we think we are going to arrive to the 2000 qubits, 1 billion gates. 2000 qubits is because we are going to have 201,000 qubits, 200,000 qubits. And this is the ratio we think we are going to achieve for logical qubits. So divide, it's like 100, more or less, okay? Our principal research during these years is going to be error correction, error mitigation. Increase in software, in middleware. Middleware is intelligent orchestration. That means that this is my field. What we are doing is analyzing the circuit, decomposing the circuit, and studying where it's going to be better executed. So you split the circuit and send to the different processors that are going to be optimal for execute that circuit. This is all the things we are going to do. Circuit nighting, which is splitting the circuit, sending to different backends that are optimum for that load. And error correction. In error correction, I don't think I'm going to have time for the last slides, but right now what we are applying is probabilistic error correction, zero noise extrapolation, twirling, and also filling with pulses, neutral pulses, all the empty spaces in the circuits. This is for the preprocessing. So then we apply the optimal execution in the quantum chip, and afterwards we apply the error mitigation with the probabilistic and zero noise extrapolation. This is our focus right now, and this is where we are going to be really focused on. These are the announcements of last year. Condor, 121, not 48. Heron, to enable couple. The system 2, as you see here, this is the quantum computer, and here you have the classical computer attached to the quantum one. We are right now delivering this, and as I mentioned, so maybe in quantum algorithms I cannot explain you so much because I'm not an expert, but we are doing these things, and I'm in charge of delivering these things. So if you have some doubts afterwards during the coffee or the beers break, just ask me. We announced the development. We announced also KC10. That means that it's a production product right now, and it's stable. When you work with beta, every 2 weeks we have changes. Right now we have a product that's stable at least 6 months. Qiskit patterns and quantumless, this is the patterns we use for use cases of deterministic or samplers that we already know, and it's going to work better. And so you can easier the way you send the circuits. Execution modes, job, iterative, or batch. When you send a job to a quantum computer, usually there is a huge queue that takes 1 hour, 2 hours, if we are talking about the free access. You can have a session, this is what we announced this year, so you can send different circuits and not do the queue all the times. So that saves you a lot of time, a lot, even if you are using it for free. And the transpilation and generative for Watson. Well, at the end, it's a copilot for creating code and also error correction based on AI. And it's working so well. We don't know why, but it's working so well. We have an entire department applying that. Usually you have a physician studying the error of the chip, and they create a map, and they calibrate that map every day. And so they create a mathematical model of the error of that processor, and you use that. And it's so many brains thinking, and then instead of that, you put all the data. You know how to put the data, but you put all the data you get in a model, you train the model, and you get better results. This is how it works. So we are focusing a lot right now on that as well. More announcements. We are going to go through this one. This is not working anymore, but only this one. This is the different access you have. The open plan, this is the one I explained. The pay as you go is the one you can go to the cloud and pay for seconds of execution. And the premium, you pay the big money and then you have big access. Quantum accelerators, these are services, and quantum safe explorer. So what I want to focus on this side, because for me this is the disruptive change of last year and this year. As you can see, every single new processor usually improve in error rate. Something that IBM and all the manufacturers of quantum and researchers are following. So the error correction. It happens exactly the same in the classical. Okay, so in the classical you have the memory. If there is some engineers, we have the CRC, it's the cycle called recovery code. So you have redundancy in the memory, because we have the cosmic particles that move the memory, and you have to recover that memory. So there are processes that make you feel there is no errors, but there are errors always. So here is the same. We have a lot of errors. Some of them comes from the cosmic rays, and some of them because there are movements in the lab. I don't know. I'm not the expert, but we are trying to shortcut that. So take that in account, and we also take in account the number of papers published until last summer. Here it's Eagle. This is Eagle. They have 127 qubits. Even with that, no one was writing papers above 20 qubits. No one in the world. And this is bad because we are not moving from the... So this can be done by simulators. In BSC, we are simulating 63 qubits with Mare Nostrum 4. With the new one, probably 64, 65, let's say. We have to... But you can do that with simulators always. You can do 20 in your laptop. But think that if you use 63, you need 2 Mare Nostrums for the next one. This is what we cannot simulate. 100 qubits. It's impossible. So last year, in summer, we published a paper with more than 100 qubits, 127. We published the paper, and a lot of people were blaming this is not true, whatever. This is always between Google and IBM and all the researchers. Whatever. But all of a sudden, after our paper in Nature, before end of September, 6 new papers, above 100 qubits. And this is what, from my point of view, what IBM is following, to have more than 100 qubits, which is what we call the utility era. To have more than 100, because with 20, okay, you are doing error mitigation, you are splitting the circuits, but at the end, you are playing with the quantum. If you are doing things above the 100 qubits, you're doing real computation that cannot be simulated. This is the difference between the circuit we published in 2017 and the circuit of last summer. It's a bunch of synods. It has not more than synods in a script, but it's a bunch of them and it was executed. This cannot be simulated by a classical. Then there were some papers that, well, since all the calculations are the same, kind of can calculate something and can simulate. But this is what we are looking. So let me explain you another paper. What time is it? Sorry. Okay, we have some time. This is the paper we showed last year in February, where before this paper, to get a logical qubit, because the rate is 99.999, you need 1,000 qubits to create a logical qubit. This was what the experts explained before this paper. After this paper, for certain errors, you can be recovered for any error, 5 errors, with 2 logical, 12, so using 23 qubits. So 288 qubits give you 12 logical qubits. That reduces the calculation a lot to 23. And that's why we put the 100,000 qubits to 2,000 logical ones. And even with that, we are conservative. We are quite conservative. So, taking this in account, these are all the papers published till today. More or less, all the papers. So, if we have 2,000 logical qubits in 2033, I'm going to show you, this is Blue Jay, this is the last one we are going to deliver in 2023, and this is its maximum power. As forecasted, 12 qubits, 2,000 qubits, 1 billion gates, 10 billion gates, sorry. This is RSA 2024. So IBM is forecasting, or let's say me, based on the data we are forecasting in 2033, RSA is going to be broken. And for me, this is the first use case. This is the first use case we are going to have. So this is a forecast of when quantum computation is going to be useful, finally, more or less. All the others are, this is optimization. This is the paper of Lacaiche, it's an optimization portfolio in its millions of logical qubits. And this is chemistry materials. So we are going to need more gates, probably, better error. And let's see, because in 10 years, probably we will have memories, we will have states, we will have different things. But at the end, I'm giving you something with the data we have today that can give you a forecast, a real forecast of when quantum is going to be really disruptive. And from now on, think, if in the 90s we were doing with a teller calculations for counting the people, and today we are with the smartphones, think about what can happen. So, well, for me, it's unmeasurable. I enjoy it a lot. I think we are on time, right? More or less. Well, if you want, this is just extra time, extra ball. Application and use cases, we have the workshops. You can see the archive and you can join these workshops. Usually we are talking only with researchers, but people can join this. And we are creating materials in HPC. I'm very linked to that. Optimization, high energy, and healthcare. This is where we are working mostly, and where we are trying to get collaboration from other research centers and companies. These are some of the cases we are researching together with companies, with Wells Fargo. They are using for fraud detection, also stocks. They are working like a JP Morgan. GSR, chemical simulators. Even if we cannot create the calculations right now because we don't have the computational powerful, we can do it theoretically, and this is why we are working with them. With Boeing, new materials as well, also new routes and simulations for engines. ExxonMobil logistics, sea movements, they are very tricky, and efficient routes mostly. In CERN, even the quantum mechanics itself, and to learn how to create algorithms and memories. And if you want to start, you have to start with Qiskit. This is the language, the standard language. I know there are other companies that are using other language, and also in UPC they are creating a new one. But I would say, based on the surveys, we do 69% of the programmers are using it. For Qiskit, the 1.0, what brings to us is how to create the circuit. So if you want to start, the first step is map the problem. You have a problem and you need to map it to a quantum circuit. This is how you start. You can map it in different ways. Let me give you an example. If you want to map colors, for example, you can use a qubit and put the vector on the area. You can define the qubit like a light color up, dark color down, for example, and you can put the vector whenever you want of the color, and you can have different tonalities of green, for example. And you can put in different qubits and work with the different colors, for example. So I'm just trying to give you an example of how you can code. If it's colors, you can code whatever information you want. And from that, you can work with that information. Once you have the circuit and the operators define it, we optimize that. Okay, and in Qiskit, it do it by yourself. This is the layer of abstraction that you don't need to have. We can do it by ourselves. And we do it with AI, as I explained you. So how we optimize, this is how we do. So in Qiskit, the error suppression, it applies before you execute the circuit. Then you have the runtime compilation. These all parallelisms you send to the correct backend. You do the split of the circuit, and then the error mitigation afterwards. Okay. This is the different optimization levels we have in Qiskit. This is the thing you can choose. So when you are coding, the optimization level field, you put 0 or 1, depending on whatever you want to do. And let me explain a little the error suppression. We already talked. The tweet readout error extinction, this is the one that you fill the gaps of the circuit that are empty. Then the minimal mitigation, it's also with the readout. The matrix free, that was this estimator and sampler. You can send a calculation with the estimation. With the estimator, you have a result. Well, this is difficult to explain. You know, when you send to a quantum computer, you can have or a result or a probabilistic distribution. Okay, it's well. With here you have the probabilistic distribution, and here you have the result. And sorry, and this is what we talk about. Zero noise extrapolation. Let me explain, because this was an idea of one Russian genius we have there. That everyone, when we move and we pass in front of his office, we say hello. If you have noise level at this point, let's say, look, this is X, so Y, X. You have this level of noise, so then you double the noise and you see the result. And then you triple the noise and you see the result. And then when you have the line, you go, you put at zero noise extrapolation the result you would have. And this is how you have the zero noise extrapolation. And the probabilistic error cancellation is the one I explained before, that a physics is doing the map of the probabilistic error of the processor, or we use the artificial intelligence. And finally, you execute via primitive, so sending the circuit, or via sampler or estimator. Go here, sign up, create your IBM ID, do it for free, and you will have 10 minutes of quantum executions, a lot of documentation, a lot of circuits, and if you need circuits or you need, I have some samplers as well. And by the way, take a picture of this one. I put a notebook on the web for you, and so you can play with the error mitigation and with the different functions. And you have also the code. So just copy, paste, and execute. Local or in the quantum lab. We have a quantum lab in the web, but it's going to be deprecated in 1 month, more probably. And that's all. Sorry if it's been too intense. Do you have any question or?
I have some questions now. Are you going to share the slide?
Some of them, yes.
So if we will share with us within a meetup, we will share them with the Analiza.
Yeah. The only one I cannot share, and I could, is the one with the papers. Yeah, we could share. We could share. No problem.
Yeah, so first of all, thank you. I wanted to ask about the topology of the chips, because up until now, all of them have that heavy hex, I think it's called, right? And in that paper that you mentioned of using the real processor, a few days later, it got simulated using tensor networks quite easily because of the the connectivity of the qubits. But you seem to keep using that connectivity. Is there a reason for that, or on why you don't move to, let's say, a more connected lattice or so?
A more connected, sorry?
More connected lattice of qubits.
Is the reason? I know the reason, but I cannot explain correctly. But the reason is there was magnetic interactions where there was too much connections. So the tunneling between the connections, it's so heavy and so noisy. So we prefer to connect only with one, as you can see, or maximum 3. But for the 3, it's only the bridges, and we prefer the snake. Yeah, this is the magnetic fields that you create connecting too much of them, and in the corners is even worse.
But then doesn't it make it, let's say,
Susceptible to classical simulators?
Yeah.
Why? I don't understand. Sorry.
For that tensor network paper that
Oh yeah.
that Romano was famously published, one of the main reasons he gave to why it was, let's say, easy to simulate, not only for 127 qubits, but for higher counts, was because of the connectivity of the chip itself. Because it didn't have many connections between and if you're saying that.
But we entangle it between different chips with the coupling.
But then the coupling is all to all, or?
Yes.
Okay.
Yes. So that's why we are separating a little, because if they are very close, yeah.
Okay, thank you.
Thank you, first of all. So my question is, in 1 year or two, there's going to be hockey stick where there's going to be a disruption. And in comparison, maybe with current LLMs where there is great potential to getting there, but maybe enterprises are underskilled to really catch the opportunities. since then, the real power to make changes is a few, and we're catching up to get people skills together. So maybe something similar is going to happen here. What would be your advice to get ready to catch that wave?
This is very difficult. I always tell the people in the enterprise that you should have already people with knowledge in quantum. The problem is the private enterprise, if they don't see a value, I mean payback value, they are not investing. Unless they are service providers, consultings like Accenture, Kilimanjaro's, IBM's. These are the companies that today they are doing. My advice for who? For the enterprises or for the employees? For both. For the enterprises is you should have someone, at least someone, that knows how to move in this field. For a big enterprise, any enterprise, sorry, that has a research budget should have someone with quantum skills. I'm not meaning that you should right now contract the people for marketing in quantum, but someone that knows a little of quantum computation, how the field is working, what's going to be the future, to prepare your company for that, that's a must from my point of view. And if you are an employee that wants to work in quantum, there are different things. In the next 5 years, I don't see a lot of work outside of the focus fields. I mean, we have people in marketing, obviously, working for quantum, and we have also designers. But out of IBM, Microsoft, Google, these kind of companies, I don't see there is going to be a lot of opportunities in these not very focused fields of the quantum side. But for algorithms and for integration, engineering integration, like the ones they are doing prompting right now with artificial intelligence, in the next 5-10 years, there's going to be plenty. At least we are hiring. We are hiring a lot of people. We feel, at least I feel the people is super prepared, like too much for what I'm looking for, like a physicist with PhDs, papers, and well, we are looking for product right now to develop product. So this is very good for the research field, only research field, or not well prepared enough. This is what I feel right now. And not well prepared enough is we are not finding people. We are not finding people in some fields. In the next 5 years, I think there's going to be a ramp up. Thanks God, the generative AI has been reducing a little the hype because we had a lot of pressure in quantum and we need some years. It's still some room for working. So yeah, next 5 years, focus. And also developers. Python developers for optimizing algorithms. And afterwards, after the between 5-10 years, explosion in all the fields for the quantum marketing, sales, even integrations, and afterwards, who knows, because that will be applied to healthcare, banking, and then it's kind of today, if you are working in a bank and you don't know how to work with a computer, you are dead. So I think it's going to happen something similar, but we're talking then 20 years, something like that. So for your children.
Last one, without getting political, Europe, US, is one of the same area.
So for me, the problem in Europe is if it's not European, I'm not buying it. And if the public money is not investing in the best technology, we are getting back. Which are the quantum computers that the European Commission has bought the last year? 5 qubits, 15 qubits, 20 qubits. So we are going to install 127 in Basque this year, and we have 3 in Fraunhofer. Next year, we are going to start installing 1,000 qubits. I've been talking with the commissioner, European commissioner, and also with Gina Tos, for example, is here, the Secretary of Digital Political Affairs in Catalonia. They know that, but they cannot spend the public money in other companies. And I told them, but spend it researching, for example, memories. There are a group in the Netherlands that works researching on memories. There is no other one in the world, and we are going to need that. There is no quantum operating system. We are working on that, but right now there is no quantum operating system. There are plenty of things that I guess we could research in Europe, maybe depending on the hardware of others. But if we create the algorithms and they depend on our algorithms, they're going to depend on us as well. So for me, it's excessively protectionist, political for European countries. I shouldn't be saying this, but it's the way I feel, sorry.
So I've always been on this quantum entanglement concept. So just to understand, is it just implementation wise used in this computing, or it's kind of considered as a real application of it, or in layman language, is it going to be considered as a challenge or boon in implementation or solving any problem?
It's something that you have to take in account. Entanglement gives you a lot of power because it's a characteristic, so you can link two qubits and they are coupled. But also something that you have to take in account in terms of it's going to be work to manage entanglement. Let me give you an example. In classical, it's very easy to send a 0 or a 1. I send a 0 or I send a 1. But it's a shared medium. So we need to correct errors because if I send a 1 and you get a 0, we are not communicating well. Easy way to do that, I send 10 ones. So I send 10 ones and you get 6 ones and 4 zeros. And you say, okay, it's a 1. In quantum, it doesn't work that way. If you have changed, there are coupling. It's not that I got a qubit in state 1. No, something is happening. So there are algorithms to solve that, but it's not as easy as it was in the classical. They are coupled, and if there is an error or you have something, you need to manage that. So entanglement gives you this kind of challenges. No, you're welcome. Siga boa.
You have shown us a roadmap and that what with blue shape or red carousel. And I think all this is relying very much, let's say, only on one interesting thing, because the people will not suddenly close all the computers they have and all the AI that is there. There is a lot of space for the interaction of quantum, conventional computing.
Yeah.
That space. What can we expect? Because maybe we could reach some of those high computing powers by combining the two without needing a quantum.
You're absolutely right. So you want to use a quantum computer for sending an email. I mean, neither for doing 2 plus 2. I don't know if 40 years, if we are so advanced. But no, the way I see the quantum, the way we see the quantum at least, is like an accelerator. When the GPUs came in the past, everything thought that was the super solution for everything, and it is not. We still have general purpose processors, we still have GPUs. Why we are not doing everything with GPUs? Could we? Maybe. But handling the memory for such kind of power is not easy. It's not easy. If you have to handle that memory between different servers is not easy neither. So sometimes it's better to work with general purpose, which has power enough for manage a database, for example, and manage much better the memory. And then for training a model, then you use GPUs because you need much more processor than memory. You need to iterate a lot. And sometimes even you reduce the register from 64 to 8 because you don't need so much accuracy. You just need to pass a lot of data. For quantum, I think it's going to be the same. It's going to be like an accelerator, like the GPUs for certain workloads. We were talking before, probably chemistry, materials, randomness, well, the ones I explained. And I think this is going to be for long years, not just in 20 years we are going to have a lot of powerful in quantum and then everything is going to be quantum. No. Last one?
Yeah, we have one last question here, and then we can continue with food and drinks before questions.
That's perfect.
One last question.
Let's go.
I wanted to ask you to tell us a bit more about your last computer. I know it's going to go in a new building there next to the IBC, and I was wondering if it's going to be more research focused or was going to be this company.
You know the buildings?
Well, yeah, I'm from the area.
You are from you know Ricardo from the DIPC? Yes, the CIO. We were talking together and I think they are going to put in the building close. At the very beginning, they were thinking on that, you know, that they had a nuclear plant close to that area. Well, on the outside of the city, but near. And we were thinking of use the reactor chamber to do that. Because you know that the seismic study for putting a nuclear central is so accurate. So there is no movements. This was perfect place. But it was not perfect for the researchers and so on. It's going to be research. They are going to be focused on research mostly. As far as I understood talking to them, they are going to embrace and motivate the local industry, Multiverse, Tecnalia, BBVA, Verola that are around, all this industry to involve them in the quantum. And I think it's a great idea because private companies probably won't put money on that until they see a real competitive advantage. But if it's the government who put the money, put the computer and give it for free for the industry and they can take advantage, they are clever. These Basque people are clever. I told the Catalan government to do the same. Gina, please. But well, we are a little more tired. I can explain the political reasons when we close the video.
Yeah, as I said, we can continue with more questions here with some food and drinks. So thank you all for joining.
Thank you all.